Section 8.2 is on page 591, talks about area of a surface of revolution. So suppose I have a function f, let it be positive and continuous derivative. We define the surface by rotating the curve y equal f of x. Let's say y equal f of x looks like this. And I'm really interested in running this from A to B. And I'm going to rotate this about the x-axis. Then this is just a wire. It's going to create an identical shape right there. And as this rotates, it's going to look like one of those, a jar sideways. Now, as this rotates, if I take a thin slice, so you know the drill by now, a very thin slice, this is rotating, and I turn that, I'll be looking at something like this. Now, I'll point out what this thickness is in a minute. So first, this is delta x, right? So if I rotate it about the x, it could be a delta x. Well, this distance, if I look at this distance, which is the radius, wouldn't that be f of x sub I depending on where this x is? Meaning, doesn't that vary depending where I choose x? It gets bigger and smaller depending on where x is. So this radius is the y value evaluated at x sub I, right? Or simply y. And if I'm talking about just the wire, just the surrounding, so when I want to look at the surface of this, this is hollow on the inside. The surface is going to be actually 2 pi times the radius, because it's going to resemble this part. That is sort of for r sub I depending on where you are, or I'm going to say s equal 2 pi times y, and y depends on x, of course. Now, one catch that comes up, no matter how thin that is, if I look at the top, do we see that? That's a horrible sketch. No matter how thin that is, if I look at this top, do you see that that's an arc? So, when I want to figure out what is the surface area, I'm gonna say S, which is the surface area of this revolution, is going to be the integral from A to B. 2 pi, there's 2 pi, y, there's pi. But when I want to say dx, I know that dx has an extra ds associated with it, right? And that's really equivalent, instead of using dx, for you to say ds, because that's an arc over this change right there. And if I revolve this about the y-axis, if I rotate about the y-axis, s will equal the integral from a to b of 2 pi x ds. Now, this ds is from section 8.1, right? We call that ds is the square root of 1 plus f prime of x dx, or it could be the square root of 1 plus g prime of y dy. Oh boy, messing things up big time. Squared. So, how am I going to do this section? Well, this section I'm going to do it the same way as I did 8.1. If you finished 8.1, once you determine I'm going to decide on ds with respect to x or y, this very annoying part would become very simple and straightforward. This is a very easy section if you understand 8.1. So let's look at some problems. I'd like to look at problem number 4. This would be on page 595, I think. 595, correct. So, the deal is, you're really going to make this irrelevant of the axis of rotation. The only thing you need to know for I, when you say, I am going to take S and rotate it about the x-axis, this is going to be a y ds. Where do I start the problem? I start the problem with ds. The integral 2 pi is a constant. I'm going to start with this square root of 1 plus a derivative squared. Before I decide, I look at this, say, okay, look, y, and guess what? It seems it's easiest to take a derivative with respect to y. That's 1 over 2y plus 1 times 2 dy. That's how I begin the problem. Automatically, now I could say that's 0 to 1. And then you decide how this works. The deal is, the tricky part in this section, should I leave this as y? Should I get rid of it? Well, if this is a delta y, then y is accepted. And if that's a delta x, then I know what x equal. A bit confusing. You'll get the hang of this. And I'm going to set up those integrals. Supposedly we could do all of those. Here it does say set up on numbers 1 through 6. But I want to do number 4 and 6 because they have both. They have dx and they have with respect to y. So if I go for the second part, s equal, with respect to y, the integral of 2 pi x ds. Now, if you did the work, you really don't have, this is not like area where you have to come in and say, oh, wait a minute, I'm revolving about, it makes no difference. If you did this already, then most likely you already decided which way you're going to go. You've already decided that, you know what, with y is the way I'm going to go, that is 0, that is 1. So it's not like parallel or perpendicular to the axis of rotation, it makes no difference. But if this is a dy, can this be an x? Well, I can't integrate, not yet, until next semester. So what does x equal in this case? Since it doesn't match, I need to write down what x equal. And that seems to be the highlight of this section. That's what most students struggle with. They try to do what they did back in the days with, oh wait, if you rotate about the x, then is that a what? You don't worry about that. You worry about section 8.1. If I was to look at this in 8.1 and say, hey, tell me what L is. Isn't L the integral of ds? If you decided to take this based on y, then that's what you do here. If you decide to take it on x, that's what you do here. And the next problem I have is also matching, but this one is with respect to. So I want to make sure that you see both cases. And I think this is one of the smoothest sections, provided you got section 8.1. So how does this work? Well, again, L equal for I about the x-axis. I'm sorry, not L. I'm stuck on L. S equal the integral of 2 pi y ds. Where do you begin? You begin with right there. You start with, since I'm glancing at this, and this is in terms of x, no need to change. I could, but there's no point. This is 1 over 1 plus x squared means dx. X equals 0 to x equals 2. I'm very happy. And can I put a y in there? Well, think about it. If this happens to be a dx, a y in there is very unlikely. What does y equal? There it is. Done. And if I decided to do the same problem using 2 pi x ds, that is rotating about y-axis, then guess what? If I did this problem already, I already know exactly how that works. I don't need to even think about it. I already decided dx is the way to go, irrelevant of whether you're rotating with respect to x or y. The only catch in this section is, can I leave this as an x, or do I write with x equal? If this is dx, x is accepted, and that's fine. And that's pretty much the highlight of this section. That's all there is to it. and you integrate, of course. But on numbers 1 through 6, it says set up the integral, do not integrate. Part B says if you have a calculator, approximate. We're not going to do that because we don't use a graphing calculator. So let me set up a couple more. Number 10, find the exact area of the surface obtained by rotated above the x-axis. S equal the integral of 2 pi y ds. Where do I begin? Well, the usual. 2 pi is a constant. I start with the square root of 1 plus, and here I am again. Same problem, ds. This is in terms of x, this is in terms of x, 0 to 1, dx, 1 over twice the radical times e to the x squared. That means what? That means, can I leave a y? Well, if this is the x, I would need to replace x by what it equals. So I'm going to try and set up 10, 12, 14, and 18 in the allowed time if possible. That would be great. On number 14, the same deal. S equal the integral of 2 pi y ds. Again, where do I begin with this? I would begin with, oh man, come on, I have to make it look pretty. ds in this case, well, look, 1 plus, and this is always, again, 8.1. I know I'm making you sick of that. I'm not going to stop. dy is the way to go. That is 4y, 1 to 2, 2 pi, and, oops, 2 pi, I already put it there. Now, can I leave the y in there? Well, if this is a dy, that's fine. If not, I will write down what x equal, and that's how it always works. I would love to set each problem both ways, but you know what the time frame we have. And if you have any questions on how to work out any of these integrals, I'll be more than happy to show you. You should practice that. Okay, the last problem I want to look at is problem number 18. And here we are rotating about the y-axis. So we know that s equal the integral of 2 pi x ds. And you could check online to see the formula that I'm going to give you on the exam. It already includes those in it. And how does that work? Again, I begin with the square root always, 1 plus. And how does that work? Well, let's see. x, it seems dx is the way to go. I might need to stretch that a bit more. The derivative of this, bring the power down, subtract 1 from the power, that's x over 2 minus. And the derivative of that is 1/2 x. And if you remember, that was the square in 8.1. I suggest you work that out. If I had time, I would work it out. Now, what's the most confusing part of this section? Do I leave this as x? Well, if this is the x, then yes. You just leave that as an x. You're done. I want to take this same problem and rotate it about the y-axis. About the x-axis, I'm sorry. X-axis. And guess what? There are a couple of exceptions, but for the most part, s equal the integral of 2 pi y ds. That is 2 pi, oh, I forgot, almost forgot, forgive me. Caspi would have nailed me on points. This guy's unforgiving. The limits on the integral are a must, otherwise we have a problem. So guess what? I don't have to even think about those. This is already set. Rotate about the x or the y. If I decided that ds is easiest by running this in terms of x, then there it is. And can I leave the y in there? Again, that's always the question. Can I leave this y in there? Well, if this is an x, I can't. What does y equal? So here I have to substitute the 1/2 x squared minus 1/2 natural log of x. If you have any questions, ask me next class time. Discussion tomorrow. Hopefully you're going to have to view those. I'm going to write the homework, and that would be it. There's the homework. Now, for my class, I don't mind if you set up all the odds and solve every other odd. I'm more interested in the setup than I'm assuming you know how to integrate, but you should really spend time on the setup.